Alright, I want to take a look now at some special problems, or I shouldn't say special, but maybe some harder problems that deal with circles. And we're going to first look at some problems that are circles with angles in them. This being one of the case, you're always asking yourself that question, where's the vertex of the angle? We went over the four types. Central angle, vertex is the center of the circle, equals the arc. Inscribed angle, vertex is on the circle, it's equal to half the arc. An angle formed inside the circle, and it's basically formed inside the circle by two intersecting chords. It's half the sum of the two arcs. And then this is an example of an angle formed outside the circle, where it's half the difference of the two arcs that it intersects. And we looked at basically two secants that intersect at a point outside a circle, a secant and a tangent, and this is an example of two tangents. And it could be something where I give you the angle 60 degrees, and maybe we're trying to find out what the arc measure is. So there's two scenarios. You're either going to be looking for the inside arc or the outside arc. Now if two tangents intersect the circle from the same point outside the circle, these two segments are congruent to one another. That's one of the theorems we went over. And not that we're going to use that theorem in this, but basically this tangent intersects a circle at this point, this tangent intersects a circle at this point. And it divides this circle now into two arcs. We're looking for the inside arc. We're going to call that x. So now if I need to come up with a term to describe the other arc in terms of x. So if this was, let's say if this was 80 degrees, we would find the other arc by subtracting it from 360. Well, in this case, I don't know what this arc is. So if I don't know what this arc is, I'm going to subtract the variable from 360 degrees. So the expression for this outside arc would be 360 minus x. So now we're going to set up the equation. The angle outside is equal to half the difference of the larger arc that it intersects minus the inside arc that it intersects. So in this case, my equation is going to look like this. The angle, 60, equals half of the outside arc, 360 minus x, minus the inside arc, which is x. So now we're going to solve this equation for x. First thing I would recommend doing is let's clean up what's inside the parentheses. So I'll bring everything down. 360, I can combine like terms, a negative x minus another x, or plus another negative x, leaves me with negative 2x. Now we talked about in some of the other problems, if you can't take half of both terms in here, one thing we could do is to alleviate the fraction is multiply both sides by whatever the denominator is, in this case 2. So we could clear the fraction. In this case, I can take half of 360 and I can take half of 2x. So I'm going to bring this down. 60 equals half of, I'm jumping the gun here. We're taking half of both terms. So half of 360 is 180 and half of 2x is negative x. Can you tilt the camera a little? Sorry, my great assistant just told me that I can't go much lower, so we're going to try and lower the camera just a hair. But now I'm going to solve this for x, so we would subtract 180 from both sides. The 180s cancel out. The negative x comes down. 60 minus 180 is negative 120. And then I could multiply both sides by negative 1 to get rid of the negative to get x equals 120 degrees. So there's an example of an angle outside the circle, which is two tangents, where I really don't know either of the arc measures. So I'll erase this and we're going to take a look at another one.
And now back to Jarvis Teaches in the Basement.
Alright, I put another example together. This one deals with, again, a theorem that involves some segments from the center that are perpendicular to a chord, what it does to the chord. And then we're also going to tie in some stuff from the last chapter with right triangles. So one of the theorems we went over is if a segment from the center, which could be a radius, a diameter, or even this, just a segment to the chord and it stops, if it's perpendicular to a chord, it does two things. It bisects the chord, meaning these two pieces are going to be congruent to one another. It also bisects the arc. That one doesn't apply to this problem. So I know these two segments are equal to each other. This segment again, from the center is perpendicular to the chord, which means it bisects this chord into two congruent pieces. And here it's asking for x. So now if I could find the length of one of these pieces, all I have to do is double it to get what x is. Now, you should note, like whenever we see perpendicular lines, we keep trying to tie in the stuff we did in the last chapter with right triangles. And what was the main thing we did with right triangles? Pythagorean's theorem. So the distance from this chord to the center is 6. This chord is 12 root 3. So if the whole thing's 12 root 3 and it divides it in half, each of those segments is going to be 6 root 3. And now I can draw in a radius, which makes a right triangle, and I'm going to be looking for the hypotenuse in this case. Well, some of you may recognize this already. I've got a right triangle where one leg is 6 and the other leg is that leg times root 3, 6 root 3. So if you remember back, what does that match? It matches the 30, 60, 90 triangle. It's one of those special right triangles that we talked about. So now the short leg 6, the long leg is 6 root 3. So to get from the short leg to the hypotenuse, you multiply by 2, and 6 times 2 is going to give me 12. Now in this case, I've got hypotenuse is 12. What kind of segment is that in the triangle? It's a radius. So I'm going to draw in another radius down here. So if the radius is 12, any other radius I draw in the circle is going to be 12 units long. Now I've got a right triangle down here. That's 12. This is 8. I need to find the third side. If I know two sides of a right triangle and I'm looking for the third side, we can use Pythagorean's theorem. Again, Pythagorean's theorem is a squared plus b squared equals c squared. What do a and b have to be? The two legs. One of the legs is 8. The other one, you can take your pick. You can call it y, you can call it x, and we're just going to have to double it. Let's call it y. So, or we can call it even b in this case. So I could put 8 squared plus b squared equals 12 squared. Now we're going to solve this for b. 8 squared is 64. 12 squared is 144. And now we're going to solve this for b. Subtract 64 from both sides. Well, what's 144 minus 64? Well, basically, if I took 44 from 64, I'd be left with 20. So I'm left with 100 minus 20 is 80. To solve this for b, to get rid of the b squared, we're going to take the square root of both sides. If you take the square root of one side of an equation, you got to take the square root of the other side of the equation. Square root of b squared is b. What's the square root of 80? So now I want to look at what factors of 80 are perfect squares. So we're trying to think, could it be 16 times something? 16 times 5 would be 80. So I can break this down into 16 and 5. Why did we pick 16? Because it's a perfect square. Square root of 16 is 4. 5 is still under the radical. So now this leg right here is 4 root 5. These are congruent. This leg's 4 root 5. And if I said I have 4 root 5s, I'm going to add 4 more root 5s to it. How many root 5s do we have altogether? 8 root 5. So now the missing chord length that we were looking for was 8 root 5. Notice this isn't, I wouldn't say an overly complicated problem, but we had to involve Pythagorean's theorem twice in this. Once we found the radius, any other radius that we would draw would be the same length. So that utilizes segment from the center, perpendicular to chord, bisects the chord, tie in Pythagorean's theorem to it, and you can find the length of another segment. We'll take a look at one more example, and then you guys should be ready for the test.
And now, yet one more example of Jarvis Teaches in the Basement.
Okay, this last one that I want to take a look at today, as we review for tomorrow's test, is a case where I got a circle, I got a segment from the center to a point of tangency, and what does that do to the tangent line? It's perpendicular to it. And we see our good old friend right angle in there. We've got a triangle. So again, we're led to believe, hey, let's use Pythagorean's theorem, or I could give you some angle measures in here, special right triangle, all that stuff could pop up. So now in this case, I know one of the legs is 5, the other leg's 12. I could look at this problem two ways, because They just want this little chunk on the outside. I could use Pythagorean's theorem to solve for the entire hypotenuse length. If I did that, once I knew it, I would have to subtract the radius from it to get x. Or I could say, if the radius is 5, what is this piece? Well, it's going to be 5. And then how long would the hypotenuse be? It would be x plus 5. One reason I don't like looking at it that way is I'm going to have to get a quadratic equation in there, and then it's going to have to, it's going to have to factor it. A lot of us don't like to factor. So let's look at this. If this is 5 and this is 12, what's the whole hypotenuse? So again, if we look at Pythagorean's theorem, a squared plus b squared equals c squared, a and b are 5 and 12, and we're solving this for c. Now some of you may already be looking at this saying, hey, if I know the legs are 5 and 12, I already know what the hypotenuse is because it's one of those Pythagorean triples. Pythagorean triple is, 3 whole numbers that, when plugged in, fit Pythagorean's theorem or work with Pythagorean's theorem. So that 5, 12, and some of you are probably in your head saying, I already know the third side's 13, and it winds up being 13. But if you didn't know it was a 5, 12, 13 right triangle, you could use Pythagorean's theorem. No two sides, looking for the third side. So 5 squared gives us 25. 12 squared gives us 144. And now we're just adding those together. We get 169 equals c squared. Take the square root of both sides, and the square root of 169 is 13. So now I know this whole side is 13. We said we already knew the radius was 5, which is this piece right here. So 5 plus what is going to give me 13? Well, again, I could set up an equation. If you don't see it, it's just x plus 5 equals 13. Guess what x equals? 8. So that's the last example I want to go through tonight that deals with just some, I don't want to say trickier problems, but things you just have to sort of look at in a different light. Again, tomorrow's test, you've got all the terminology with circles: radius, diameter, chord, tangent, secant, how to name a circle, how to name arcs, minor arcs, major arcs, how to deal with degree measures with arcs, and then all the stuff we did with angles, broken down into 4 pieces: central angle, inscribed angle, angles inside a circle, angles outside a circle, and same thing with segments, all the stuff we did with segments. Segments that intersect inside a circle, segments that intersect outside a circle, 2 secants, and if it was a secant and a tangent, or 2 tangents. And then other than that, we've got, again, the theorems that went with all this chapter. And if you look through all your day 1, day 2, day 3, day 4, day 5, and day 6 notes of circles, we saw a bunch of theorems that apply to what happens when a segment from the center is perpendicular to a chord. What happens when a segment from the center goes to a point of tangency? What does it do? What is it if it's perpendicular to a chord? What does it do to the arc? What about the opposite angles of a quadrilateral inscribed in a circle? All those things apply here. So hopefully you study, you look over your notes, and you guys will do well in the test. See you tomorrow.